sphere. It has a radius r and a spherical hole of radius a inside at the position shown. So here's a sphere, it's an insulator, it has a uniform charge density rho, and inside the sphere is a little drilled out sphere with radius a. Find the magnitude and direction of the electric field somewhere inside this hole right here. So we can solve this problem. It seems pretty tough, but let's try and look at it in light of the problem we just did. What we did already was we found what's the electric field inside a sphere that is off-centered. And if we think about that in context of this problem, here's a sphere that's off-center. We already sorted out what the electric field inside there was due to its own contribution. So let's see if we can put it together and figure out what is the electric field inside this structure. So let's do another drawing and let's think about how can we best represent this. So here's a sphere which has a little hole drilled out. We could think about this, and we'll shade that in to show that it's a hole. We could think about this as a whole sphere, subtract a smaller sphere. Okay, so sphere with a cavity equals solid sphere minus the tiny offset sphere. So now if we can find the electric field of this solid sphere, and we know the electric field of this smaller sphere, if we subtract those two guys, it's going to give us the electric field of this structure. So there's our strategy for this problem. So let's see what we can figure out here. Let's put a coordinate system down through the center of this solid sphere. So there's a coordinate system. We'd like to find the electric field at some position r. And that position r is going to be relative to the origin. And so we can think about superimposing that sphere on top of here, and that origin is at the center of this sphere. And we have our smaller sphere here. We know that the electric field of this one, relative to that origin, we can even put that guy on this picture if we want. So that vector r right there, we know that this one, E of r, is equal to the density times r minus b divided by 3 epsilon naught. So that's the electric field inside that solid sphere. Whatever this electric field is, if we subtract this much, we'll get what's left over, which was the problem we were asked for. So let's try and find the electric field inside this solid sphere. It's going to be a lot like what we did in the previous problem, but let's go through the steps anyway. So we'll write our Gauss's law. The integral of E dot dA is equal to Q inside over epsilon naught. So that's the integral of E dot dA. So this is the integral of E times dA times cosine of 0. Our Gaussian surface is a sphere with radius r. The electric field points out, the little area element points out. So that's E outside the area. Integral of dA, which gives us E times A, which is E times 4 pi r squared. Okay, we did that in the previous one, so I won't write out all the steps here. And then for our Q inside, that's the density times the volume of the Gaussian surface. So that's the density times 4/3 times pi times r cubed. Let's put those guys together and get the total electric field inside that solid sphere. So E times 4 pi r squared equals rho times 4/3 pi r cubed divided by epsilon naught. 4's and pi's cancel. E is equal to rho times r over 3 times epsilon naught. Electric field is a vector with a direction. The direction of the electric field is radial. It points in the r direction. So the electric field vector, E, is equal to rho times r hat over 3 epsilon naught. Magnitude of r times the direction of r is the vector r. Rho rho times r over 3 epsilon naught. Okay, so my electric field inside the solid sphere is rho times r over 3 epsilon naught. The electric field inside the small sphere is rho times r minus b over 3 epsilon naught. If we subtract those guys, we get the electric field inside the sphere with the hole. So let's fill in those guys. We have rho times r over 3 epsilon naught. Take away rho times r minus b over 3 epsilon naught. We can simplify that a little bit. So that's rho times r over 3 epsilon naught minus rho r over 3 epsilon naught. Minus times minus is plus, rho times b over 3 epsilon naught. These guys cancel and we're left with rho times b over 3 epsilon naught. That's the electric field inside the cavity. So we're confining our r to inside the cavity. E inside cavity.